All right, welcome everybody. So in this video, we are going to continue our work with looking at models, doing some machine learning, in particular, doing some regression. And I want to consider fitting a quadratic model to the following example, where we're going to have one predictor variable, which is the launch angle that a baseball player hits the ball when they're batting. And then the response variable is going to be the distance that ball travels. And again, if you're not kind of familiar with the context here, here's our baseball player. They hit a ball, maybe it travels in this direction. This angle right here is what we're considering the launch angle, and then we're going to measure as a result of that how far the ball travels. And we may not want to use a linear model in the sense of excluding this squared term, because linear models either are always increasing or always decreasing at a constant rate. And based on the behavior that I can observe in this data, as we increase the angle, the distance goes up at first, and then the distance starts to decrease. So it's not as if every time I increase the launch angle, the ball is going to travel even further. If I have a really large launch angle like this, the ball tends to go up and come back down and not go very far. So we've constructed a quadratic model previously that included an intercept term. The model I want to consider now is what if we just consider the quadratic model where we set the intercept equal to 0. So here our model is going to be that the distance that the baseball travels is equal to some coefficient beta 1 times the launch angle plus some other coefficient beta 2 times the launch angle squared. And because this model is linear in the betas, we can solve this by using the least squares solution to find the best fitting quadratic model for this by taking our model matrix X, taking the product of X transpose X, inverting that times X transpose times our matrix or our column vector of observed distances. So this is what we're calling Y. So our model matrix and vector Y I've now recorded here. And this model matrix is different than the previous quadratic model that we set up in that now I no longer have a column of ones because we don't have an intercept term. So each of these angles we multiply by beta 1, and then each of the squares of the angles we multiply by beta 2. So our model matrix consists of one column of angles, one column of angles squared, and here's our column vector of observed response values. And these are the only two things that we need to enter into Colab in order to calculate our solution. So there is a link to a Colab notebook where all of these calculations are done in the description to this video. So here's my matrix X and Y. I plug them into this formula, and you can verify the calculations in the Colab notebook. But then what you get is that beta is approximately, the beta 1 value is about 12.75. So that's what goes in front of the angle. And the beta 2 value is minus 0.15, and that's what goes in front of the angle squared term. So according to this model, we would get that the predicted distance is equal to 12.75 times the angle minus 0.15 times the angle squared. And so let's take a look on the next slide about how we can compare this quadratic model to the previous quadratic model that we constructed that had an intercept term. Okay, so let's kind of summarize how we can compare various models for the following data set, where we've observed the launch angle for 5 different hitters when they hit the ball, and then we recorded how far that ball traveled. And we would like to come up with a model that is going to be able to accurately predict the distance that the ball travels based on its launch angle. And we've already talked about why a linear model may not be a good choice, because here you can see are the data points. And these data points, what we can see is at first, as we increase the launch angle, the baseball does increase its distance, but at some point the launch angle gets too big and we just get a pop-up and the ball, actually the distance that the ball travels, starts to decrease. So you can check the Colab notebook linked in the description of this video to see where this model came from. But here we can see that this model plotted in green is going to do a really bad job of actually fitting the data, and it's not going to do a really good job at making any predictions for us. So looking at this data, we can see that it seems a little bit quadratic. At least the graph looks like a parabola. So let's try and figure out what's the best parabola that we could fit to this data. And so the first quadratic model that we came up with included an intercept. And so that model I've written over here. And that's the graph that's drawn in blue. And so when you're doing regression, you definitely want to be taking a look at visually what these models are doing. So I can at least really clearly, I don't need very fancy metrics here to just look at this data and say, this blue curve is doing a much better job than that green line is doing at making predictions, or at least at trying to predict the known observed values that we have. We also constructed a quadratic model that had no intercept, and that did not change these other coefficients very much. And then we can take a look at how that model fits the data, and it's pretty similar. And so these two would be really hard to compare just by eyeballing them. So we may need some other metrics to compare these two, and maybe there are other variables that we might want to include, or a different model that might make more sense. So this is a really interesting, intriguing field, data science, machine learning. We have an entire course in regression analysis. We have an entire course in machine learning. So these are very robust fields. But I hope you're getting a sense for how pivotal a role linear algebra plays in this process. And we've actually constructed some models pretty quickly just by taking products of matrices and using Python as a powerful computational tool for doing that.